In this video, we're going to continue to learn about the concept of work. We'll also derive the important work energy principle, and through that be able to define the formula for kinetic energy. We'll also look at what do we mean by power. Let's review a problem that we did last time. A man pulls a child on a sled with a force of 10 newtons at an angle of 30 degrees for a horizontal distance of 5 meters. How much work is done on the sled? So as we did before, we said that the work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. And pretty quickly, we found that the work done in this case was 43 joules. We talked a little bit about where does that energy go? Well, it can go into a couple places. It can go into kinetic energy and also into thermal energy. So let's look at that in a little bit more detail. If we continue the problem, it says if the magnitude of the force of friction acting on the sled is 2 newtons, how much work is done by friction during the 5-meter pull, and what is the net work done on the sled? So first of all, just for review, let's draw a free body diagram of all the forces acting on the sled. We know that there's the normal force, there's the applied force that our person is exerting, there is the force of gravity acting down, mg, and there is also the force of kinetic friction acting to the left. The first thing then we want to do is figure out what is the work done by that force of friction. So notice this is not a free body diagram I'm drawing over here. I'm just drawing that the force is to the left and the direction of the displacement, delta r, is to the right. Notice that that angle between the force and the displacement is 180, and it's always 180 degrees for friction. So we can now go ahead and figure out what is the work done by kinetic friction in this case. It's just the force of kinetic friction times delta r times the cosine of the angle between them. Again, when you plug in here, what I want to make sure I see is that you put in the magnitude of the force, so that's 2 newtons, the magnitude of the displacement, which is 5, and then the cosine of 180. That's where the minus sign is going to come from. Do not stick the minus sign in here, because remember, in the formula, F and delta R are magnitudes. Okay, when you calculate that, you should get negative 10 joules. So that's the work done by friction. Now, remember, when we do work on an object, we're either giving the object energy or taking energy away. Friction takes energy away from the sled. Let's go ahead and figure out what the net work is on the sled. By the way, there are really two ways you could do this. You could figure out the net force and then figure out the work done by that net force, or we can look at the work done by each of the forces separately and then add that up. Either way, it's the same. But since we already know the work done by Fa and the work done by friction, let's write this out this way. The total work or net work done is just the work done by friction plus the work done by the normal force plus the work done by gravity plus the work done by our applied force, the man pulling the sled. Which of these forces do we know are equal to 0? Well, hopefully you realize that both the work done by the normal force and the work done by gravity are 0 here. And remember, the reason that is because in both of those cases, theta is either 90 or negative 90. In other words, for the normal force, the angle between the normal force and the displacement is 90, and the angle between the force of gravity and the displacement is negative 90. And that's why both of those are 0, because we're taking the cosine of 90 or negative 90 degrees. And therefore, the net work in this case is only the work done by friction, which we said is negative 10 joules, and the work done by our applied force, which we figured out previously to be 43 joules. And therefore, the net work was equal to 33 joules. So that's the total amount of energy that the sled gained in this process. So where does that end up? Well, that ends up entirely as kinetic energy. And one of our goals in this video is to define the formula for kinetic energy. But the sled now has energy in the form of motion that it didn't have before. One other thing we need to talk about in terms of work before we can move on and talk about kinetic energy is how do we calculate the work when the force is not constant over the displacement? So it turns out those two formulas that we have for calculating work, whether we have the magnitudes of the force and the displacement and the angle between them, or whether we have the components of the force and the displacement, those formulas are only valid if the force is constant over the displacement. If the force is changing throughout the displacement, so think about, for example, a spring. As the spring gets displaced, the force is increasing. Well, we can't use these equations if the force is changing. So let's look at how we deal with a varying force. Well, one of the things we can think about is that if we plot force, and really it's the component of the force in the direction of the position, if we plot force versus position, you'll notice that if we have just a constant force, then you quickly notice that the work is basically the area under that graph. It's just the force times the displacement. And again, that's really the component of the force in the direction of the displacement. So we can now kind of come up with a way of calculating the work if the force is changing. Really all we need to do is we need to be able to estimate the area under this graph. And so you could probably come up with a way to do that. For example, we could figure out kind of average values of the force over small amounts and add up the area of all those rectangles, and that would give you at least an approximation of what the work is. It turns out, though, that there's actually a way to do that with calculus, and that's by taking the integral. So if we know the function that describes the force, then the integral of that function is equal to the area under this curve. Now that's really a topic of Calc 2, and in this course we're only assuming that you're concurrently taking Calc 1. So I'm not going to have you do any integrals because you don't in general know how yet. But what I do want you to understand is that an integral simply allows us to calculate the area under a function. Just like we know that when we take the derivative of a function, it allows us to figure out the slope at any point along that function. Okay? So the work is the area under the force versus position graph. And even though we're not going to use integrals in this course, that means if we can plot the force versus the position, we can figure out the work done by that force. Let's look at an example of that. Let's figure out how much work is done to stretch a spring. So here is the spring in its equilibrium position. And let's say that we stretch that spring a distance x. Now we know that the spring is going to exert a force back in this direction. So the force that we have to apply to pull the spring would be in this direction. We'll call that Fa for an applied force. And if we're just stretching that spring with a constant velocity, then the force that we have to apply to stretch it is just kx. In other words, it's equal to the force that the spring exerts. So let's calculate the work that we do to stretch the spring a distance x. Well, here's the force. Let's plot that versus position. You'll notice that what we get is a straight line. Notice the slope of our graph is just k, the spring constant. And what we now want to do is figure out how much work do we do in stretching that spring a distance x. Well, again, that really is just a matter of figuring out what is the area here. Well, this point is kx. And so what we want to do is we want to find the area. We know the area is going to be kx times x divided by 2, or 1/2 kx squared. And therefore, the work to stretch the spring a distance x is 1/2 kx squared. Now, for those of you who know how to do integrals, you'll notice that you can find that same result by doing the integral from 0 to x of f of x dx. In other words, the integral of kx dx from 0 to x, and you'll get the same value. One of the things that is important about this result is if that's the amount of work that we do to stretch the spring a distance x, where is that energy now? Well, it's stored in the spring. And so we'll see in the next chapter when we talk more about potential energy, we're going to see that this is the expression for the potential energy stored in a spring. Because if I do work on the spring to stretch it, I've now given the spring that energy, so the spring is storing that amount of energy. We're now ready to derive our first version of a very important principle called the work-energy principle. The work-energy principle gives us a relationship between the work done on an object and the kinetic energy gained. Again, we know kinetic energy is the energy of motion, but we don't yet have a formula to describe it, and that's what we're going to figure out here. So let's look at the following example. We're going to exert a net force on this car. So again, there could be multiple forces acting. Normal force, gravity, an applied force, a force of friction. But overall, the net force acting on this car is to the right. And we're going to let the car go through a displacement. And what we want to do is figure out what is the net work done on the car and what does that equal? Well, the net work is just going to be equal to the net force, again that's the magnitude, times the magnitude of the displacement, times the cosine of the angle between them. Notice in this case, both the net force and delta r are in the same direction, so that's just the cosine of 0. Therefore, the net work is just equal to the net force times delta r. What I now want to do, though, is use Newton's second law and rewrite this. We know the net force is just equal to the mass times the acceleration. So I'll write ma delta r. At this point, what I want to do is I want to rewrite A in terms of velocity. And that's because ultimately, if kinetic energy has to do with motion, it should be tied to an object's velocity. In order to do this, I'm going to use one of our kinematic equations. Remember, we know that v squared is equal to v naught squared plus 2a times x minus x naught. Notice, though, x minus x naught is just what we now mean by delta r. It's just the displacement. So I'll rewrite that, and I'm going to bring the v naught squared to the other side. So I have v squared minus v naught squared is equal to 2a delta r. Or a delta r is equal to v squared minus v naught squared over 2. I'm going to now take that and I'm going to plug it in for a delta r. So we get that the net work done is equal to m over 2 times v squared minus v naught squared. I'm going to rewrite that as the net work is equal to 1/2 mv squared minus 1/2 mv naught squared. And that's where we wanted to get to. So think about what we've just found. We found that the net work is equal to something that's changing. Notice here's our final value and our initial value. So in fact, we define kinetic energy as 1/2 mv squared, and we can see that when we have net work done on an object, the net work is equal to the change in kinetic energy of the object. So just to summarize that, what we found is that the kinetic energy, and by the way, translational kinetic energy, I'm usually just going to say kinetic energy, but we're distinguishing it from rotational kinetic energy, which we'll talk about in a much later video. So the kinetic energy is defined as 1/2 mv squared, and what we've just derived is called the work energy principle. And what we found is that the net work done on an object is equal to the change in its kinetic energy. You'll notice that I put a note that says not yet complete. We'll add to this in our next video. Soon we will replace this with WNC equals delta K plus delta U. And in a later video I'll tell you what I mean by NC, and we'll talk about delta U. But I'll just let you know that delta U is all about potential energy, which we'll talk about soon. But for now, here is our work energy principle. If there's net work done on an object, then the object is going to either gain or lose kinetic energy based on whether the net work is positive or negative. Let's try out a problem using this new formulation. A car has an initial velocity of 20 meters per second. What's the net force necessary to accelerate the car to 40 meters per second in a distance of 100 meters? The mass of the car is 1,500 kilograms. So we now want to use the fact that the net work is equal to the change in kinetic energy. That's our starting point, the work energy principle. So let's go ahead and first draw a picture of what's going on. We've got our car. It's moving with an initial velocity of 20 meters per second. Its final velocity is 40 meters per second. And it's covering a total displacement of 100 meters. Okay, so let's go ahead and figure this out. The net work is just the net force times the displacement times the cosine of the angle between them, and that's equal to the change in kinetic energy. In other words, 1/2 mv squared, the final kinetic energy, minus 1/2 mv naught squared, the initial kinetic energy. We can go ahead then and solve this for the net force. The net force is just going to be 1/2 mv squared minus 1/2 mv naught squared divided by delta r cosine theta. In this case, since the net force is to the right and delta r is to the right, we can see that theta is going to be 0. I'll leave it to you to go ahead and plug in the values, but what you should find is that the net force comes out to be about 1,000 newtons. Could we have done this problem before we'd studied energy? Definitely. In other words, you'll notice that all we would have done is we would have first used kinematics to figure out what the acceleration was in the problem. And then once we have the acceleration, we could have found the net force by just using Newton's second law. So we definitely could have done that problem by using Newton's second law in kinematics. So right now, it's probably not apparent why this energy method is any better than what we knew before. And the answer to that is it's isn't really until we add the idea of potential energy. And that's what we're going to do starting in our next video. One of the other things I wanted to mention, when I derived the work energy principle, I used kinematics to do it. And the reason I did it that way is I wanted to use something that you were already familiar with. However, it's very important to understand that the work energy principle, which is really just a way to write conservation of energy, the work energy principle is true whether the acceleration is constant or not. So it's a more general solution than kinematics is. Okay, so the work energy principle is true whether the acceleration is constant or not. Let's look at one last quick thing in this video, which is power. In everyday speech, we often kind of interchange the words power and energy, but they definitely have very different meanings. Power is the rate at which we do work, or more generally, the rate at which energy is being transferred or used. Remember, work is just how we give an object energy, so work is energy. Well, average power is the amount of work we do per time. Instantaneous power is a derivative. So it's just the rate at which we use energy. That's what power is. Let's look at the units of power. You'll notice that looking at the formulas, we can see that power has units of joules per second. And because power is such an important concept, we define the watt as a unit for power. So a watt is equal to a joule per second. Let's look at a quick example. You'll notice that light bulbs are rated in watts. So if I've got a 100-watt light bulb, what I now know is that that light bulb is using 100 joules of energy for every second that it's turned on. So if you have a 100-watt light bulb and you have it turned on for 10 seconds, you've just used 1,000 joules of energy. Go ahead and try this last problem. A typical car battery stores 4 times 10 to the 6 joules of energy. What is the power output if you leave your lights on and the battery drains completely in 2.5 hours? Okay, so we want to figure out the amount of energy that the battery provides. It provides 4 times 10 to the 6 joules, so that's going to be delta W, 4 times 10 to the 6th. Now, how much time? Here we just have to be a little bit careful with units. We know that we want power to be in units of watts, and that's a joule per second. Therefore, we've got to take our 2.5 hours and convert that to seconds. We know that there are 3,600 seconds in 1 hour. So that'll get rid of hours and leave us with seconds in the denominator. And if you calculated that correctly, you should have gotten 444 joules. Sorry, 444 watts. So in other words, 444 joules per second is what the battery was providing. In our next video, we're going to introduce the concept of potential energy.